recording has started again. So you're all famous again?
Yeah.
Alright, so module 7 is Ethernet switching. So this is what switches do with the frames that we just looked at in chapter 6. So here we'll have a look at how the Ethernet frame is made up, how the MAC addresses work, how switches build a MAC address table that it uses on decision making on how to forward frames, and we'll look at the two main forwarding methods used by switches within Ethernet. So Ethernet is one of the protocols that runs at layer 2, and it is a combination of 802.2 and 802.3 standards. So Ethernet, the 2.3 is the MAC sublayer down, and 2.2 is our logical link. You may need to know those for a chapter test question, I'm guessing. Alright, saw this slide basically in the last chapter, so I won't go through it again. MAC sublayer 802.3, it is relevant to Ethernet frames, how Ethernet addressing is used, and how some frame check sequence information so basically CRC check basically is used to detect errors on frames. So the MAC sublayer is the one that has all the various elements of 802.3, and they address specific media types. So you've got U for fast Ethernet, Z for gigabit Ethernet over fiber, AB for Ethernet over copper at gigabit speeds, and AE, etc. for Ethernet over fiber at 10 gigabits. So each media type will have its specific subset of 802.3 that addresses how it addresses and is encapsulated and transmitted on that specific media. Okay, frames are a minimum of 64 bytes and a maximum of 18 bytes in length. So if you have a frame less than 64 bytes in total size, it's considered a collision fragment or a runt. Alternative, if frames are 1500 bytes and more, then they're considered jumbo frames, and not every device can handle jumbo frames. So basically, frames are dropped if they're too small or too large. Okay. So our MAC address is expressed using hexadecimal numbers. It is a 48-bit binary address. It is split in half. The first half represents the vendor. The second half represents the actual individual card itself. Okay. Cast your mind back to chapter 5 to do the binary to hex conversions, and I'll post up a worksheet this week for you to do some practice conversions on, just to keep your hand in, because we will be needing it in chapter 11 when we do IP addressing. You'll need that binary to decimal conversion big time at that point. So this is our unique organizer. So basically this is our vendor identifier, and then the second half is our unique vendor assigned. So each card that goes through manufacturer gets one value added in the vendor assigned, and basically we can do searches on specific OUIs, the vendor portion, to work out what type of devices are connected into the network, for example. Frame processing, pretty much as we just went through that. I won't spend a great deal of time here. So the way it works is the frame is placed on the cable and every device sees it, and it looks at the destination address, and if it is not, okay, for in this example, H2 looks at it, CCCC is not my address, so I ignore the rest of the frame. H3 picks it up, looks at the destination address, oh, that's my address, so I will action the frame because it's specifically for me to do something with. So it de-encapsulates the frame, passes the data up to layer 3, and then goes back to listening to the cable. We have a few different ways these addresses work, and they are unicast, broadcast, and multicast communications. We've touched on that earlier with the types of addresses that we need. So a unicast MAC is only going to go to a single device, thus the unicast. Okay, whereas a ARP request would go out to many. It's a broadcast, so it's basically sending it out to everybody to pick up and look at the IP address to see what is happening. We'll look at the ARP protocols and the other protocols as we go through. Broadcast MAC addresses, where very simply identified, all the binary bits are set to 1. So FFFFFFF. Okay, that is a broadcast frame. Every device on that medium will pick it up and action the frame. Multicast is where it's basically like a subscription service, if you like, where multiple devices are part of a group and they only want to transmit the information once to the entire group. So we use multicast addresses, and basically what we do is we set the frames to a specific address range that tells the devices that it is a multicast frame, and if the host is a member of the multicast group, it'll pick up the frame and check to see whether it's part of each group. I should probably point out there that 01005E is where we set those addresses to. Switching fundamentals. Okay. The MAC address table is known as Content Addressable Memory, or CAM table. That is its formal name. MAC address table is its de facto name. I like how they say, oh, it could be sometimes referred to as. CAM tables were what it was officially known as, and if you look at any of the documents, early documents, it always refers to a CAM table, because the content addressable memory function is not just applicable to Ethernet, which MAC address table is specifically to Ethernet. So switches use content addressable memory, CAM tables, for layer 2 addressing, forwarding, okay, regardless of the Ethernet or another protocol in use. And basically how it works is, as a frame arrives, it records the source MAC address and puts it into the table, and it says, okay, that frame arrived on port 15, so I'll have that MAC address associated with port 15. So when a reply comes back for that MAC address, it knows to forward it out only qubit 15. Okay, so it learns MAC addresses from the source, and Ethernet switches, when they power on, will by default go into learning mode, so they'll listen and learn from the packets, from the frames, and then it will build this MAC address table, and it'll keep the entries within the table for a maximum of 5 minutes. Once that timer has expired, it removes the entry from the table, thus conserving memory and keeping the table current. Each time a frame arrives, it resets the timer if it's the same combination. Forwarding is based on the contents of the address table, so it looks for the MAC address in the table. If it finds a match, it will only forward it out the port that it has in the MAC address table. If it doesn't find a match, it will forward it out all ports except for the port it was received on. So it basically floods it out to every other device on the network. Okay, so this is basically what they call filtering. So when it comes in port 1, so we've got a destination MAC address of 000D and a source MAC address of 000A. So when it comes in port 1, it'll record 000A and reset the timer. So what's 5 minutes? 300 seconds? Sound about right? So timer reset. It'll then look at the destination MAC address and look down the table and see if it has a match. If it has a match, it looks at the port number, so it will come in port 1 and go out port 4. Two methods of forwarding are store and forward, or cut through. Now, store and forward means it will store the entire frame, do the CRC check, and make sure the frame is valid, and then make a forwarding decision on the entire frame. Whereas cut through waits essentially for 64 bytes to make sure it's got the header information and it's not a collision frame or fragment, and then will forward based on the partial header that the 64 bytes gives it. So it's got enough information to make a forwarding decision based on that waiting. And as it receives the frame, it is sending it out. Big advantage of cut through is it is so much faster than store and forward. The bad side is it doesn't catch any corrupted frames as they're passing through. So store and forward is quality of service analysis, and that requires the whole frame to arrive so it can do a full analysis on the frame before doing classifications and things like that. So horses for courses.
And whiskey for my men.
Hey?
Oh, sorry, no, it was wrong song.
Horses for courses, wrong song?
Yeah, no, I said whiskey for my men.
Oh, okay. Don't know it. Sorry, not off the top of my head.
I think it's a Willie Nelson song. No, or is it?
Okay.
Don't worry.
I just, my memory for actual artists and song names are terrible.
Beer for my horses, whiskey for my men.
But if I start listening to it, I can recognise the song or not. But ask me what the song's name and the artists are, no, can't tell you.
Yeah, no.
Beers for my horses, there you go. Yeah, that definitely sounds like a Willie song.
I'm not a huge fan,
but he was a character.
Willie
I'm
does.
from the generation that can appreciate him. Whenever he did acting roles, he was always the stoned out hippie type.
Yeah.
He's certainly a character.
I learned that in Dukes of Hazzard.
Yep. It's pretty much that part that he played in just about every TV show and movie that he played.
Yeah.
Pretty much he played himself.
Yeah. Yeah.
So, memory buffering, we have two sorts. We have port-based memory allocation, which means every port gets a fixed amount of buffer space for that port and that port only. And then you have shared memory where all the ports use the entire allocation of the buffer on a first in, first out basis. So the benefits of port-based is you've got dedicated buffering for that port. There's always some allocation there for each port to buffer frames. Downside is it's not as efficient as shared memory. In other words, if a port is using more traffic, it needs more buffering than ports that don't have as much traffic. So, yeah. But basically the way it buffers is if it's busy transmitting or receiving a frame and it has to start forwarding, the frame is transferred to the buffer for that port, and once the port has finished doing the transmission or receiving whatever action it's currently doing, it goes to the buffer and takes the next one in the queue out of the buffer and starts sending it. Now, there is a big difference in speed when we talk about half duplex and full duplex. If you've got 100 megabits per second at half duplex, you basically can have effectively 200 megabits on full duplex, because it can send and receive at 100 megabits per second. Same with the gigabits. So full duplex basically doubles your available bandwidth, if you like, the speed that can be sent. Gigabit Ethernet only operates in full duplex mode. Just be aware of that. So it's only on the older kit that you'd have this duplex mismatch and that occurring. So basically, if it's fast Ethernet, you could have a duplex mismatch. If it's gigabit, it's got to be set to full duplex, and if you're getting a duplex mismatch, go look at the fast Ethernet end. So what happens in a mix match is one says I can transmit and receive and I can do it much better. The problem is on the half duplex end, it's going, whoa, what are you doing transmitting while I'm transmitting? I can't do both at the same time. And what occurs is it can't agree on the setting, so it ends up flapping between up and down, dum, 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 as it can't agree from one end to the other. So the way to fix that is you go in and change one end to full or half, whatever it is, you set it. Because generally it's when both ends are trying to auto-negotiate and they fall out of sequence to each other and they flip back and forth. Auto-MDIX is basically the system that detects what type of cable you have connected into the port. Remember T568A and B connections, it will detect what wires are basically connected into the port by sending a little message down the cable and getting a response. Do not rely on this for all your solutions. Basically, if you know it's a crossover cable but you need a patch lead and you can't find a patch lead, then use it. Otherwise, use the correct cable types. It will just make life so much simpler for you, because when you go to fault find and it's an Auto-MDIX problem, has it got the right cable in it or not? You don't know because it's freaking out. I should be able to use crossovers for this. So if you stick to the old rule of thumb, use a patch for a patch and a crossover for a crossover. If MDIX is giving you trouble, you know it's not going to be the cable, it's actually the software. Okay, it just eliminates one of the problems. And that comes sadly to the end of chapter 7. So we had a look at how Ethernet specifically handles layer 2, how it uses different sub-modules within LLC and MAC sublayers depending on the media type that it is being using for transport. Okay. We have a MAC address, which is the layer 2 address, which is 48 bits in size and is expressed using hexadecimal digits. The first 6 of those represent the vendor and the last 6 the unique number from the vendor. So what's that OUI, was it? I think you may need to know that. Okay, so we then looked at forwarding decisions, how it uses a MAC address table to record the port that the frame is received on against the source MAC address, and then makes forwarding decisions based on that table. We looked at the two methods of store and forward and cut-through switching, and the quick pluses and minuses of those two methods, and port-based or shared memory buffering and the quick pluses and minuses of those. And duplex and half duplex basically only affects anything under gigabit. And that is the end. You can all wake up now. All right.